All right. So now please let me ask Department of Production and Automation, and the session will be chaired by Tomáš Kratěna. Please go ahead.
Thank you. So good afternoon, everybody. So let me quickly introduce our department. So we are basically four parts in our department: machine processes and control, led by Professor Vyhlídal. Then there is efficient production, led by Peter Kolář, and simulation, optimization, and measurement, led by Professor Valášek. And lastly, last but not least, prototype workshop, led by Dr. Smolík. The three last parts are based in the heavy test bed, so in the down floor of the test bed, and the activities are in the field of novel robotics application, industrial robotics, production machines, and manufacturing processes. So today we will present, or there will be three papers presented. First one is about a single rod Brachiation robot, mechatronic control design and validation of pre-jump phases, and the presenter will be Professor Vyhlídal. So if I may ask you to start, please, and present the paper.
Hello, everybody. Thank you for staying till the end. Yeah, my name is Tomáš Vyhlídal, and next to being a bit affiliated to CERC, I am mainly affiliated to Faculty of Mechanical Engineering, Department of Instrumentation and Control Engineering. And actually, I'm going to present a paper, a single rod brachiation robot, mechatronic control design and validation of pre-jump phases, which actually was prepared in collaboration with Tokyo University of Agriculture and Technology. Actually, the origin of our collaboration is through the author Hajiri Akahane, who was a master student in the group of Professor Iko Mizushi, and spent, I think, three months study stay here in CERC, and during his stay, he actually worked on this topic. Yeah, so he built the single rod robot. Can I move here, or better? Yeah, okay. Yeah. Yeah. So the actually scheme. Can you see it? Yes. Sorry. The scheme of the single rod robot is here. Yeah, so it's a really very simple structure here, which has two grippers, and the objective is to move with the center of gravity, to make it swing, and if we gain enough energy, so we should grasp or get to the following bar.
Imagine an ape jumping from one branch to the other one.
Yes, so this is the brachiation motion. Yeah, so so we have, but actually, ape has multi-link body. Yes, so I think 1, 2, 3, 4 link, which is a bit easier. Yeah, but with a single link, it's a challenge. Because if we go back, and if we just look at the problem from a classical control theory point of view, yes, so the system is non-controllable. Yeah, because if you linearize it in the position, whatever position, yeah, so you cannot get a controllable system. Yeah, so only option is to really control it like a nonlinear system here through nonlinear control algorithm. Yeah, I should mention that we don't use any AI or neural networks. Yeah, so it's classical control theory. Yeah, so we know, maybe just to mention, yeah, that the paper was published in IEEE semi-transaction on Mechatronics, which is one of the best journals in the mechatronic topic. Yeah, so here is actually the robot which was built by Hajiri during his master thesis, and he brought it here, and actually here Valášek put us together. And coincidentally, we worked on a similar problem. Yeah, so we, but in an inverse. Yeah, so we just we had objective here to dump the oscillations by repositioning the gravity center. Yeah, so it consists. Yeah, so here is the rod. Yeah, the center of mass, which is being repositioned by crank-slide mechanism. Yeah, and here we have two grippers. Yeah, so the visualization, yeah, how it works. Yeah, you need to actually precisely reposition the mask either in the turning points or in the central point. Yeah, to get the motion. Yes, so as I have mentioned, yes, so we consider two phases. Yes, so the first one is the swinging phase. Yes, so if we are in the turning point, yes, so we need to take the mass here from this position to the other. Yes, so which makes the momentum larger, and if we are in the central position, yes, so we just turn it up. And if we the repositioning. Yeah, the frequency of repositioning is obviously double frequency of the motion. It changes if you have the rotation phase, yeah, so which is visualized here. Yeah, and this is the first experiment performed by Hajiri when he returned from Zurich to Tokyo, and it was in the first version of the paper which we published. Yeah, so you see that it works, but the reviewers also wanted to see the other stage, yeah, the rotation. Yeah, so so we have a bit improved. Yeah, the mechatronic parts, yeah, the motors also adjusted the gripper. Meanwhile, Hajiri defended his thesis and left university, and his work was taken over by Auto Osawa, who is working on the topic now, and actually he spent also I think 3 months with us last year. Yeah, and this is the result. Sorry. Yeah, so this experiment was done here in Prague. Yeah, so Auto brought the robot again here from Tokyo to Prague. Yeah, so the robot traveled a lot during the development and finalizing the paper. Yeah, so the video doesn't start. Yeah. Yeah, and of course, because we know the oscillation period, yeah, so you can thought that it would be easier, relatively easy to reconfigure the mass if we do it double frequency. But due to keeping the synchronization of these two motions, we need to involve the feedback control. Yeah, so we have 2 levels. In the first level, we have a set point generator, and in the lower level, we have the control of the servo, yeah, which compensate all the nonlinearities. Yeah, so now we are in the swinging phase, and in a while we will switch to rotation. Yeah, but connection is through the wires. Yeah, so we still need to switch it off in the right moment. Yeah, so these are these are the results, and Auto now continues on the work with a bit more sophisticated construction of the Brachiation robot. And we thank you for attention together with Professor Ikuyo Mizushi. Actually, this collaboration has also given me opportunity to visit him in Japan. You can see Fuji Mountain behind us. Okay, so thank you, and thanks also to RoboProx.
Maybe, yeah, question?
It's I can confirm. Yeah, this last semester we hosted another student, and 2 other students are going to go to Japan.
Thank you, and the next speaker is Rytíř. So I will just...
So hello from my side. I would like to present our research in the technology of large-scale additive manufacturing, of large-scale 3D printing. My name is Rytíř, and I am from the Department of Industrial Production and Automation. Maybe you know better this department under the name Lower Testbed. So in the lower testbed, we have this robotic cell, which consists of multiple robots, and this research is focused on the orange one, on the KUKA robot, which has the extruder and is able to do 3D printing in a large scale. What does it mean? The most interesting part of this robot is the 3D printing head. So this 3D printing is a bit similar to the Prusa printing, to the table printers, but it works with the pellets, not with filaments. So it enables to print large scale with high output up to 18 millimeters nozzles. But this research was focused on a large scale of thin walled parts. So it means we are using just 2 millimeters nozzles and printing thin wall structures. The main question in this technology is how to ensure optimal bonding of the layers to have good structure and good mechanical properties. Yeah, so you can see the part which we focused on. It's a thin walled part, which we called structure part, because it's a part of laser cutting machine. It's a core which is used for carbon fiber winding to prepare the final beam. So it's a core of this final beam for the laser cutting machine, and we would like to ensure the optimal mechanical properties of 3D printing part. And the main question is how to do it, which process parameters influence this mechanical properties, and we would like to quantify the influence of setting these technology parameters to the final mechanical properties. So this is our technical equipment. You can see the robot, but behind the robot there is of course some control. It's a, let's say, special kind of control concerning in the industrial robots, because it's a CNC control robots. We use the numeric CNC. So basically the robot has a high level of continuous part control of the robot, and this is the important point for 3D printing, because basically it's a continuous part controlling of the robot. This approach of the control enables us to use the standard programming process. We have CAD, we have CAM software, and we are able via Siemens NX generate the G code, which we are able to run on the robot. CNC control enables us good setting of the detailed parameters of the path control, and it's much more complex than the standard robot continuous path control, like we know from the industrial practice. So, something to the design of the experiment. As I mentioned, we focused on the thin walled parts. So we printed three same parts, but there were some constant parameters and some variable process parameters. So we use 2 millimeters nozzle, some layer height, some layer width, and some layer length. So it is the length of the one layer. But every part was printed using different layer time. Layer time is it's an important parameter in a large-scale additive manufacturing, and it's a time of printing one layers. Why this is important? Because it is connected with the temperatures, and the temperatures is a key parameters for the bonding of the layers. So layer time, it's a good parameters, but the temperature matters. So we also measure the temperatures. We selected some discrete points on this structure to check the consistency in a cooling, and to check the temperature on a straight walls, on the edges, and so on. So based on this thin wall part, we prepared equivalent part for one important reason, because we would like to prepare the specimens for the tensile testing. And it's much more easier to prepare the specimens from the straight walls, because we would like to be effective, but the equivalent part has the connection to the previous structure part, because it has the same layer length. Yeah. So basically, the temperatures on the straight walls should be the same, and we cut out the specimens for this equivalent part from this wall. It's illustrated on this picture, and of course there is some anisotropy in specimen. So we select the direction of 45 degrees, 0 degrees, and 90 degrees. So pretty straightforward. After cutting out the specimens, we go to the tensile stress testing on the testing machine, and we were able to check the mechanical properties of each specimen. So if you can remember, we had three parts with the different layer times, and from each of these parts we cut out 3 different specimens with different orientation. So a lot of part for testing. Of course, there were some repeats in the testing to have some statistical value behind the experiment. But here we have the sum up of the results. So 2 main points are important for us. We evaluated that the anisotropy in tensile strength is important. So there is a drop between the mode of the loading. So when we have the 0 degree and 90 degrees, so this you can see the diagram. There is a very high drop in a tensile strength. We can expect this, but we would like to evaluate the value. And second result of our experiment, it's really important for us, because we would like to know how important is the layer time concerning the tensile strength. We need to know the value. We know that this is important, but it is not clear how important it is. So the result of this research is this number. We can see that when we have the shorter layer time, the bonding of the layers is better, and we can see that there is a 44% drop in tensile strength when we have the higher layer time. So the layer time was 20 seconds, 25 seconds, and 30 seconds. This is some process window where we can move, and when we have the short layer time, just 20 seconds, we have, of course, the best mechanical properties, and we know that when we compare it with the 30 seconds, the difference in the tensile strength is 44%. This is our output from this research for us, and there is some conclusion. We know that we have to focus on temperature control of the layers, because it matters and it is really important for final mechanical properties of the part. We know that the direction of the load is important, so sometimes, and of course also for this thin wall part, we have to decide if we would like to maybe print it under the direction concerning the final load of the part. And it's still ongoing research. Right now, we installed thermal cameras on the extruder to have the information about the temperatures at the end of the nozzle. And right now, we are trying to put it in the feedback to the robot to have somehow the automated production process. Yeah, so this is all from my side. Thank you for your attention. If you have some question, don't hesitate to ask.
Maybe I will ask you then, what is the biggest part that you can print with the printer?
Yeah, it's a large scale. What does it mean? For example, we are able to print up to 2 meters workpieces. So in comparison to a standard table 3D printer, it's really large scale for us.
Thank you. And the last presentation will be by me. So allow me to present this last presentation about the research that we did and the paper that we published last year. It's about workpiece position optimization in robotic multi-axis machining. So the paper was posted in the results in engineering in summer, and it focuses on robotic machining. So maybe you know that CNC machines are normally used for machining, for example, metal parts, but also wood parts, plastic parts. So we were trying to use robots to do the machining. But there is one major disadvantage, and that is the stiffness. So industrial robots usually have lower static stiffness, higher dynamic compliance. So some papers suggest using stiffness models to find the optimal configuration of the robot or of the workpiece. But mainly these models are using only one parameter per each joint. So each joint has only one torsional stiffness considered. So that is the standard approach to the static stiffness modeling. So what we did, we tried to model the robot with more parameters. So basically each joint of the robot had all 6 stiffness parameters, so 3 directional stiffnesses and 3 torsional stiffnesses. And moreover, each of these parameters could also depend on the specific joint configuration. So it could change while the robot was moving. And then we wanted to calculate the directional stiffness value based on the force that is acting on the robot flange or on the tool. So we first needed to measure the stiffness parameters. So we used laser tracker, and we put reflectors on 2 adjacent links for each joint, and then we were able to model the deformations in the joints for different configurations, and based on that we were able to make the stiffness model. So here you can see, for example, to illustrate that it's not desirable to neglect the other parameters. Here, so if there is a force in the y direction, and we are looking at this picture on the deformation or the twist in the second joint, in the axis that is perpendicular to the main joint axis, we see that it's quite the values of the twist are quite high, so they contribute to the overall deformation of the robot. So if we neglect them, then we lose a lot of precision in the model. So it's not desirable to neglect those parameters. Then we needed to build a stiffness criterion that we wanted to use in the optimization. Basically, we wanted to calculate the directional stiffness in each point of the tool path. And we needed to make the criterion so it would also penalize, for example, the high oscillation in stiffness. So that's why there are 2 parameters of the criterion. And also it must not depend on the number of points in the tool path. So when we had the criterion, we designed an experiment of machining. We machined aluminium. It was a 5-axis operation, 5-axis contouring operation on this spherical surface. And we used genetic algorithms to find an optimal position of the workpiece in the robot, in selected robot workspace here. But in order to compare it with something, we also find what I will call like a non-optimal position, which is basically we switch the sign on the criterion, but we still remain some constraints in the algorithm, as if the robot needs to be able to reach the position and also to not be in a singular position during the motion, but also to have lower stiffness or directional stiffness in that position. So that 2 positions we used to basically find the interval where we can get the parameters of the machine surface. So here you can see the progression of the stiffness in the optimal position and also in the non-optimal position. And we were focusing on this red square basically, which is represented here on the workpiece, which had the major difference in the static stiffness, in the progression of the static stiffness. So there you can see the machining experiment. So the first one is the optimal position found in the certain workspace, and the second one is then the non-optimal position that we use to compare these two positions. So these are the results that we got. It's quite clear to see that there are major differences. For example, the data in the upper half of the table are from Alicona's scanning microscope, so you can see some parameters of the surface. And in this parameters SA and SQ, which are the parameters of the basically square surface, you can see that there is like 5 times difference between the optimal and non-optimal position. The second table is from the CMM machine. So these are the parameters of the precision. And also you can see, for example, the measured radius in the optimal and then non-optimal positions are quite different, and in the optimal it's better, as well as the circularity. So these results gives us an idea how much these parameters can change in the robot workspace, and motivates us to use approach like this when we are using robots for machining to find out the best possible position of the workpiece and also the configuration of the robot to, for example, meet the criteria that are required for a certain part to be machined with robot. So thank you for your attention. That's all from my side. So if there are any questions, I'm happy to answer. Thank you.